Dear committee members, good morning. I am Vishwam, Faculty of Physics, Geetham University, Hyderabad campus. I did my MSc Physics from Shadan PG College, affiliated with Usmania University, and secured second rank. I obtained my PhD in Physics from IIT Madras under the guidance of Professor B.R.K. Murthy and Professor B. Subramanian in the field of dielectric relaxation spectroscopy of liquid samples. My research area includes the broadband dielectric spectroscopy of biological samples and protein solutions, the microwave characterization of materials like solids and thin films, the quantum chemistry and molecular polarizability calculations. I published 50 research articles in the peer-reviewed journals and one patent and one book chapter. I represented my work in various research platforms like international and national conferences. I'm passionate about my teaching and curious about learning and sharing to the students community. Basically, my family is in teaching profession. My father is a retired Telugu headmaster and poet. During my 7th standard, I attended one of the science exhibition near to my school. In that expo, one of the professors explained the working of rocket and Pascal's principle and some light experiments. These experiments helped me a lot to take my decision to pursue physics as my career. During my PhD days, Professor K.V.S. Ramarao, Professor T.S. Natarajan, and Professor V.R.K. Murthy observed my teaching skills in undergraduate labs as well as the doubt clearance for BTech students. They advised me to take the teaching as a profession. After finishing my PhD, I joined in FITGI Delhi, which is the Institute for IIT JEE aspirants. The most of the students are selected in the various IITs. This job helped me a lot to understand the concepts thoroughly. During the time, I didn't get sufficient time to carry further my research. I resigned my job, joined in Geetham as assistant professor in 2010. Most of the students who are joined in engineering students feel that physics is only to clear the entrance exams and board exams, and most of the students are scared to learn the physics. They're thinking that what is the role of physics in engineering? I discussed the same with my professors and they asked me to think further to teach the concept effectively so that they start liking it. I implemented experimental teaching in the classroom and cleared most of the doubts in the classroom. I used to watch Professor Walton Levin's lecture from MIT and use the PhET labs visualization effectively in the classroom. Slowly, students are learning the subject and they're curious to know and they're sharing the concept among the students. And I used to explain that how the things work in the classroom, the live demo mode like induction stove, working of microwave principle, and the magnetic loop train and the superconductivity experiments. Initiated the science and seminars and invited the experts in the field to deliver the talks in the campus. I am always thankful to the Geetham management for supporting and encouraging this type of things in the campus. I used to teach engineering physics and solid state physics, semiconductor physics, advanced quantum mechanics, and condenser matter physics for BSc and BTech students. I have attended one workshop on blended learning using ICT tools by IIT Bombay. I have learned the flipped classroom methodology during this workshop and created a small 2 minutes video and sharing to the students. Students are going to the video and discussing among the groups. Then they're sharing their knowledge. I used to move out around the classroom to clear the doubts. This activity helps a lot for learning the things. We organized Science Expo consecutively 4 years. We developed 300 working models with the support of BTech and BSc students. Average 7,000 students are visited this particular Science Expo. During the COVID period, I have led the team of the bridge course related to the introductory concepts. As a social responsibility, I used to teach the weekend classes for near government schools and involved in the development of Science Museum in the district headquarters. I received Best Teacher Award and SAP Award of Excellence and Best Paper Award from IIT Kharagpur. Thank you. Dear students, today we are learning the Hall effect experiment. The main purpose of using this Hall effect experiment is to find out the type of charge carriers of a semiconductor as n-type or p-type, and the number of charge carriers in a given semiconducting material and mobility of the charge carriers. This experiment consists of have taken a semiconductor of dimensions A, B and D. So here let me assume the x-axis is the y-axis and this is said to be the z-axis. For the semiconductor, I am following the current along the x-axis. Then apply the magnetic field perpendicular to the current. So what happens? I am assuming it is a p-type semiconductor. Let us consider I am assuming the p-type semiconductor. The majority carriers are holes. So what happens? The direction of current is in this direction. Electron flow will be in the opposite direction. Because the charge carriers are holes, there must be a force acting on a charge carriers. So anyone knows about Fleming's left hand rule? Can you explain? Yeah, please come and explain. Fleming's left hand rule. F, L, H. Fleming's left hand rule.
In Fleming's left hand rule,
No. Yes.
thumb finger shows the force F, B,
Correct.
and force, magnetic field and current. In this here, force is acting upwards, B, magnetic field and current is
In this
magnetic
direction. So there must be a force acting on the charge carriers. Everyone hold the finger like this. This is the direction of current. We are applying the magnetic field along y-axis. There must be a force so that the charge carriers are holes shifted to the upward direction. So what happens? The positive charge carriers are here, negative charge carriers are here. The majority charge carriers are holes. There must be a potential which is developed perpendicular to the current and the magnetic field. This potential is said to be the Hall potential or Hall voltage. If this Hall voltage shows a positive sign, it indicates p-type. If it indicates negative, it shows n-type semiconductor. So I am defining now. Let us consider a semiconductor, pass the current along x-axis and apply the magnetic field perpendicular to the current. There must be a force which is acting on the charge carriers perpendicular to the current and the magnetic field. So due to that force, the charge carriers are drifted upward direction. So this potential is said to be the Hall potential. If it shows positive, it shows to the p-type. If it shows negative, it is going to be the n-type. So this is about the Hall. So here the electric field force is balanced with the magnetic field force. So let us consider the Q is the charge carriers. The force acting into the electric field, I can write Q. With respect to the magnetic field, Q VB cross B. This VB is said to be the drift velocity because the velocity applied to the charge carriers in presence of electric field. This is said to be the drift velocity. The velocity and the magnetic field both are perpendicular. So the angle becomes 90 degrees. This becomes I write Q B B B. So I can cancel Q and Q. I get Q. Because there is an electric field is developed between this and the EH. So this I write as EH equal to VB. So here I am defining the current density. The current density is equal to, I write equation number 1. N is the number of charge carriers, Q is the charge, Vd is the drift velocity. If I write Vd as J by Nq, equation number 2. If I substitute this in here, I get EH equal to J by Nq times of B. So I can write EH by JB and calling as a Hall coefficient RH equal to 1 by L times of K. This is said to be the Hall coefficient. This is said to be the Hall coefficient. So for a semiconductor, the number of charge carriers are more, so that RH will be less. For metals, N will be more, RH will be less. For semiconductors, N will be less, RH will be greater. So this is about the Hall coefficient. The next part will define the Hall voltage. I am using this relation EH. The Hall electric field can be written as potential at this level B. J is nothing but current density like I by A into B by N. I like I B J N Q. The A is nothing but area. I will take this particular portion for the solution. B, so I, B, B, T, and let's move. So B H by B. So B will be cancelled. So I got Hall effect voltage on the form. So current, magnetic field, thickness, and number of charges. So this is about the experiment. Now I'll experimentally demonstrate. I'll take the semiconductor, I'll do the process, pass the current along x-axis, field along the y-axis. Let me see the result observing the experiment. Let's see. So this is the semiconductor, the small piece, what I've shown in the semiconductor. We are passing the current along the x-axis, placing the perpendicular magnetic field. There are two opposite points, nothing but to measure the potential, which is connected to this. So the black and red color shows for the current. This yellow and green nothing but measure the voltage. So what I will do now, I will insert between the two core pieces perpendicular to the current. Now, so this is the setup to measure the magnetic field between the two core pieces. It's called digital Gauss meter. What I will do, I'll pass the current through the coil. There is a magnetic field produced between the two Ds. So I'll increase the current through the coil. I kept 2 amperes. Let's see, I kept 2 amperes here. The current passing through the coil is 2 amperes. So let's see what's the magnetic field. When place here, so it shows how much the magnetic field. 3.38 kilo Gauss. So this is the magnetic field between the coil. So the magnetic field is. So what I will do, I'll pass the current through the semiconductor as per the class. So what we discussed so far, I'll pass the current. You can see this. It's showing 0. And if you increase the current, you can able to see the potential. See this. This shows the positive sign. So it indicates is a p-type magnet. So the current is increasing, the potential also increases. This is one fact. So you can see the current is increasing, the voltage also, potential also increasing. So what I will do now, I'll increase the magnetic field. I'll keep both are fixed, current is fixed. The voltage is 42.7 millivolts. I'll increase the magnetic field. Let's see how much is variation. Look at this. Voltage also increasing. Okay, can you try once? Can you try this? So 2 times, increase the current. You can see the change. Is it clear to you? So this is an Hall. So by using this Hall effect, we are able to identify the type of charge carriers. We have to go for the complete process. We can calculate the number of charge carriers. Okay, thank you.
Welcome to the teaching in Geetham. The following courses that I have taken so far for BTech students: Engineering Physics 1 and 2, Principles of Electromagnetics, Principles of Quantum Mechanics, Physics of Nanomaterials, Semiconductor Devices and Circuits. For especially BSc students, the Mechanics, Waves and Optics, Electromagnetism, physics of nanomaterials, thermal physics. For MSc students, semiconductor physics and electromagnetic theory. I use the flipped classroom methodology in the classroom effectively for especially engineering students. In this methodology involves think, pair and share. I was to send a 2 minutes video prior to the class. Students will go to the particular video and I'll make a small groups in the classroom. So they think individually, then they'll share the information in a group to the group. I used to go around the classroom. So whichever they are saying, finally I'm written on the board, which is correct, which is not correct. I'll discuss concept wise so that the students are able to understand the concept clearly. And it is an active learning in the classroom so that each and every student is engaged in the classroom. Then the experimental teaching in the classroom. I have to do the live experiments in the classroom for effective learning. Apart from that, I have used the virtual lab for especially lab programs in the COVID time, the FET simulations for visualizations, Wolfram Alpha, MIT blossoms regularly in my classroom teaching. Welcome to the research. My research area is focused on the broadband dielectric relaxation spectroscopy. So what it is meant by broadband dielectric relaxation spectroscopy? I'll try to use to explain very simple way what is exactly the dielectric spectroscopy. Here I'm taking a material which is maybe a polar material. When an electromagnetic wave is propagating through this material, certain part of the energy got absorbed. Why there is an absorption? There is a polarization mechanism taking place in the material. So there is a phase lag between the polarization and the electric field which causes its attenuation. So the dielectric constant nowhere a real value, it becomes a complex quantity. Means it consists of real value as well as imaginary. Because we are dealing with the frequency, it becomes a complexity. If it is at the static level, it is said to be the dielectric constant. So with respect to the alternating frequency, the dielectric constant becomes a complex. So based on the dielectric laws which is associated with the relaxation of molecules. The meaning of relaxation is nothing but the time taken by the molecules to attain from one equilibrium position to the other equilibrium position. Especially in the microwaves, the relaxation comes only due to the orientation polarizability and it depends on temperature. This relaxation time, the typical relaxation time is around picoseconds. For water, 8.97 picoseconds. Based on the relaxation mechanisms, the molecular dynamics can be studied and understood, and what type of intermolecular interactions are taking place, and what's the conductivity and interfacial polarization between the surfaces. And also this relaxation time depends upon the size, shape and dipolar interactions. Especially in the biological systems, for time domain relaxation spectroscopy, it comes under gigahertz region. So this is the water, this is the amino acid region and proteins. This region I am interested. Why have considered these dielectric materials, especially for biological materials? Because our body contains the proteins. The protein consists of amino acids. These amino acids consist of OH, C11O, and amine functional groups. These particular functional groups get connected with the hydrogen bonds. So the hydrogen bond plays an important role in cell building, synthesis of hormones and neurotransmitters. So the study of hydrogen bonding and nature of molecular interactions plays a vital role in the enzyme catalysis, drug synthesis and the electrical properties of the material. So if you observe this particular structure, which I said earlier, all these functional groups connected with the hydrogen bonds. These hydrogen bonds are dynamic, which changes with respect to the frequency, with respect to the temperature and environment. So my focus is to understand the nature of intermolecular interactions exist between the compounds between A and B, or maybe the compound which is dissolved in a water medium. Especially for the when your protein is dissolved in a water medium, if you propagate the electromagnetic waves of wide frequency region, maybe the megahertz region to the gigahertz region, something is going to be happen. Here, this graph explains about the dispersion mechanism of molecules of different relaxation mechanisms. This beta dispersion is only due to the protein with a bound water, whereas this delta is only due to the water surrounding with the tissue or protein. This gamma relaxation is only due to the protein relaxation. This delta region is very much important to understand the bound water phenomena of protein or tissue. It will give the wide information about the association of tissues with the water molecules. If you observe this particular figure, the applications of broadband spectroscopy, there is a tumor, this is the breast cancer. So when you pass the electromagnetic waves, this particular tissue absorbs certain radiation compared to the healthy tissue. If you reciprocate the image, we can get how depth it is there and what is the environment, how much percent of the tissue got infected. These are all the things can be studied from the molecular structure and relaxation and conductivity behavior. That is the reason I have chosen this particular area of interest. If we know the structural properties and relaxation conductivity, I can able to say that how much percentage it got damaged. So this is applications of broadband dielectric spectroscopy. At presently, I am developing a biosensor which is based on the polymer matrix, which can able to sense the sugar levels and the amount of moisture content in the agriculture products, and also the conductivity mechanism of protein solutions for the biological applications. These are the achievements. After joining the Gita, I have published around 48 publications in the peer-reviewed journals and 2 papers are in review, and I got 1 patent and 1 book chapter. So I used to publish in the Journal of Molecular Liquids, Spectrochemical Acta, and Molecular Physics, Molecular Structure. I have done some part related to the liquid crystals and also published in the Chemical Physics, Indian Journal of Physics, Indian Journal of Pure and Applied Physics. I'm reviewer for some of the journals. I obtained one project as a co-PI with one of my colleagues, Balakrishna, Chemistry Department on nonlinear polymers. I have got a seed grant from the Geetham. I have completed this work. These are the awards: Best Paper Award, Subject Matter Expert, and SAP Award of Excellence, and Best Paper Award, and Best Student Award, and Best Paper Award from the IIT Kharagpur. Thank you.